Hello and welcome to Video Notes 4.7. This will be our last notes of Unit 4. And so we're going to talk about paired inference. So for the next units, we're going to actually be talking a lot more about inference where there's two samples from different populations. But this unit, we can still talk about paired data here. So that's this one special type of data that comes from technically two samples. It is called paired data. And so here's an example of where we can use some paired data. So in many countries, developed countries, women tend to live longer than men, and thus their average age is higher. However, the opposite is often true for married couples in which the wife tends to be slightly younger. Consider the data for 16 randomly selected British couples shown to the right, which comes from a large random sample of 170 British couples for which the ages of the couples are reported. So before we get started, what we want to do is actually, since this is paired data, okay, like this is like a matched pairs sort of idea, we want to actually deal with, instead of two different samples, we're going to deal with a single sample that represents the difference. In this case, husband minus wife. So take a moment and fill in that right column in the table for the difference. So here is our differences over here in the column. Take a moment to pause and check all of your answers. So since this is paired data, okay, that means that the observations are collected in pairs, like we've done here, husband and wife that are married to each other. This can occur when one group is naturally related to the other group, such as before-after treatments. That's a pretty common one with matched pairs, sort of like placebo versus taking the actual treatment. So the two groups are not independent of each other, okay? That'll be something we talk about next unit a lot, about if we're getting two samples, they should be independent of each other. Here, they are not independent of each other. And so we're interested in those differences. So that's why we're listing out the differences in all of these rather than treating them as two separate sort of samples. So as we continue along here, what we need to do is check our conditions. We're going to be using a T model. You should pause and think about why a T model makes sense here and not a Z model. But we're going to check our conditions, and we have a new one that we're going to check out here, which is called the paired data's condition. Cool. So it says exactly what you are thinking there, like paired data condition. What are you checking? We're just checking and writing down explicitly that we're dealing with data that is in pairs, paired data. So in this particular case, yeah, we're dealing with paired data by husband and wife. So we're just going to state that explicitly there. Okay. Let's go ahead then and think about the other conditions, though. Take a pause and think about what they are. So the first we're going to do is randomization. So it says up above that is a random sample of 16 husband and wife couples here. It's randomly selected. Independence, we're going to assume, because the 16 is likely less than 10% of all British husband-wife couples. So that seems fair to say. I'd say there are probably more than 160 husband and wife couples in the United Kingdom, British. I don't know the difference, actually. Last one we need to check is for normality. This one I'll leave for you to think about because we're dealing with T model here. So remember, there are three different ways that you can do this, but often there's only one way actually that makes sense for the given context. So take a moment, pause, review the three different ways and figure out what's the one that we're going to want to use here. We'll talk about it when we get into class. All right, so when we're doing this, we need to Look at the observed average difference of the pairs. So we've taken all of our data here and we've created it in terms of differences. Instead of two different sort of samples, we're dealing with one sample, the difference of ages, husband minus wife, which we are going to go ahead and call D bar. Instead of X bar, D bar, D for difference. And so we're going to find the average of our differences there from those 16 differences up in the table. To do it, you're going to want to use your calculator, okay? You could add them all up and divide by 16 if you wanted to, but remember your 1var stats in your calculator can find this plus other very useful stuff for us in just a moment. So go ahead and pause the video and do that on your calculator and we'll come back. So you should have found a D bar equivalent to 2.6875. All right, next step, we're going to find the standard error for the sampling distribution of D bar. So again, even though these are two different samples, and next unit we'll talk about when you have two samples, how you find standard deviations and errors. Since we're using them as a single difference though, we don't need to worry about that yet. And we're going to do it just like we did in 4.6, lesson 4.6. I also think we did this in lesson 4.2 as well. So to find the S sub D bar, the standard error of the sampling distribution for D bar, we're going to take the the standard deviation of our differences from our sample and divide that by the square root of our sample size. So that's S sub D, that is also from your 1var's stats. If you're still looking at it, you can see that S is equal to 3.9953. It says S sub X on your calculator because, well, your calculator defaults to using X as the variable name, but here we're using D. Don't worry about it. It totally is the exact same thing. And we're going to go over the square root of 16, which should get us a value of 0.9988, almost 1 there. So our differences are separated from the mean by about 1. All right. And then the degrees of freedom. So just like in our one sample t interval and our t-test, we want to calculate our degrees of freedom. Take a moment to think about how we do that. So recall that that is just n minus 1, which in this case, 16 minus 1. So our degrees of freedom is 15 in this scenario. Great. So we are ready now to move on to thinking about calculating our our interval here, which is going to be a 95% paired t interval, which you can see the formula right over here. It has the same exact structure as we're used to. You've got sort of your point estimate here, the mean of our differences, plus or minus t star value times the standard error. So what I want you to do right now is pause the video. I want you to calculate and construct this interval. And then I want you to also write your conclusion. Once you're done, go ahead and unpause the video and you will see my answers given here. So here is my interval and my interpretation of said interval. So first, the interval, the main thing we didn't go over that you had to figure out on your own was your t star value. Remember, you can find that on your t table here. So what's our degrees of freedom? What confidence level are we at? So you should have gotten that as 2.131. And then our interpretation. So this one, I sort of, you could stick to the sentence frames that we've been using and sort of plug in. This one I got a little more creative. So we are 95% confident that British husbands are on average older than their wives between 0.5591 and 4.8159 years. So it's basically saying the same thing as what we usually say, but I just sort of phrased it differently since we're comparing husbands to wives in Britain. All right. Let's move over to the backside now. So on the backside here, we're going to talk about a hypothesis test. You can also do hypothesis test with paired data. When it's paired data, we call it a paired t-test. And so we're going to use that to determine whether there's sufficient evidence to reject the null hypothesis in favor of an alternative. In this particular case, we have 2 samples we're working with, but we're going to treat it like 1 sample with those differences. So it's going to sort of harken back to lesson 4.2. So let's take a look at it. But a lot of this is going to be all on you to work through and try out on your own. So here we go. Some drivers of cars that run on regular gasoline instead try to buy premium gasoline with the belief that they get better gas mileage. To test that belief, we use 10 cars in a company fleet in which all the cars are designed to be able to run on regular gas. Each car is filled with either regular or premium gasoline, decided by a coin flip, and the mileage for that tank full is recorded. Then the mileage is recorded again for the same cars for a tank full of the other kind of gas. We do not let the drivers know which type of gasoline they have in their car. Is this strong statistically significant evidence at an alpha level of 0.01 that cars get better gas mileage with premium gasoline? So there's the data that's given to you there, okay? And you should know what to do with it. We're gonna let you, well, I guess I'll give you this hint, is that just like on the interval on the front side, when we found our interval, we started with finding the difference. That's how you should start as well, is find those differences between the gas mileages, and then sort of use that through your t-test. So don't forget to state, plan, do, and conclude on that. So go ahead and pause the video for that. Now that you've unpaused the video and hopefully finished those things on your own, I want to point your direction toward the last question there, which is, do you think this test proves that everyone should be using premium gasoline? So that kind of gives away the results from this. Hopefully you concluded some significance, statistically significant evidence. So does that prove that everyone should be using premium gasoline? Why or why not? I want you to sort of think about that. That's sort of an extra question for you that we can talk about in class as well. So finish up this backside as much as you can, and we're going to check it off. We'll talk about these questions, and we'll see you in class.